Very good. So here's a brief summary of our last few classes. So the first thing we want to be able to do is intuition tells us that there should be a definition for this thing, a1 plus a sub 2 plus a sub 3 plus a sub 4. And again, I'm not going to go into this, but we did a bunch of examples and we showed you that this sort of has an intuitive thing in our head, be it our decimal system, be it me drawing that square and cutting it in half, then cutting it in half and cutting it in half forever and ever and ever. Intuition tells us that there should be a way to define this properly. And so it turns out that we call the above sum, and I use the word sum very lightly in quotations, we call the above sum an infinite series. And so for short, we typically write it like this. We say the sum, the k starts from 1 to infinity, and then we have a sub k, and that's a sub 1, plus a sub 2, plus a sub 3, etc. Now, what we recognize is that we can classify different series. That's what we recognize. Let me go back because some of you might not be done. Okay, so what we decide to do is we do in many sort of aspects of life is we classify things. So what we found is some types of series are quote unquote easy. And when I write easy, I don't mean they're easy like you're stupid for not getting it. I mean easy relative to the general scenario. So some types of series are easier to study than the general case. So what were the two that we pointed out? One is called a geometric series. And these look like this. They are some number raised to a power. So this would be r plus the number r squared plus the number r cubed plus the number r to the fourth, etc. And the other type we saw just on Tuesday that were quite easy to study, these were called the p-series. And these looked like this. A p-series looked like 1 over the index raised to some power p. So this would be 1 over k plus 1 over k. Excuse me, I wrote that wrong. K is the index, so this would be one plus 1 over 2 to the power p plus 1 over 3 to the power p plus 1 over 4 to the power p, etc. So why do we say these are easy to study in quotations? Because they have a very obvious form, number raised to power. Here it's 1 over number raised to power. But the subtle difference between geometric and P is, notice the powers in a geometric series are the index, where R is some fixed number. So it's very important that you understand that here R is a number. And here, down here, P is a number. And depending on what either R or P are, we readily know right away whether it converges or diverges. And what's even more awesome is the fact that with a geometric series, not only can we tell you when it converges, we can tell you what its sum is. And I'm not going to state that again because we've done it numerous times and we're going to do examples soon enough. Well, actually, it's -1 and 1. You're forgetting the negative values, Zafalgar. So again, it's important that you understand. You don't have to apologize. That's called learning. The good thing to keep in mind is that these ones are, again, if you understand their definitions and you understand their basic properties, they are easy. Now, in general, things are not easy. I don't want to use that. So, in general, it is not quote unquote easy to study an arbitrary series. So let's remind you that when I write a sub k, I am not saying anything specific about these numbers. All I'm saying is I have a number plus another number plus another number plus another number, etc. So what we do is we develop a series of tests. So we develop tests that we use to determine if the series converges or diverges. So here's where we're at, and this is a very sort of common theme in areas of science. I have a series, this blue guy right in front of me. I have a number plus a number plus a number plus a number. Now, it doesn't fit the pattern of geometric, and it doesn't fit the pattern of a P series. So I don't know what I can say about it. So it turns out that usually the best I can do is I can say it either converges or diverges. So let's remind you of the tests that we have already sort of written down. And they are as follows. So far,
can you go to the previous page?
Yeah, sure. You have a question or you just copying?
Oh, just copy.
Okay, take your time. We are in no hurry. Well, maybe you are. I don't know. Can't even go outside and play because it's rainy.
I'm done.
Good? Very
Yep.
good. Okay, so far we have stated the following test. The first one we did was the integral test. Then we stated what we called the divergence test. And then we had, after the divergence test and integral test, we had the so-called comparison test. And then we also had what's called the limit comparison test. So we stated the last two on Tuesday, and then the first two we did last week. I think someone had something they'd like to say. No, it sounds better when you say what a time to be alive. And this is what you say, Wattbot, what a time to be alive. And then what I will do is I will take a picture of this because it's fun to do this. And then everyone I can show my friends and they will enjoy the fact that we have fun in math class. See, isn't this fun? Now, what does that say? This is what? This is what? You got to get better.
I think he's saying this is hard.
Oh, this is hard. Okay. Very good. Look at this. You have interpreters. You have people speaking on your behalf. You're like a leader, Zafalgar. You have a spokesperson. Like, you know, the president has those people who go out and talk on their behalf. That's what you have. All right. Insulted? How are you insulted? That's good. You have a spokesperson. That means you're like a celebrity. All right. Very good. So what we need to do now is we need to do a couple more tests, and then we need to just do examples. Okay, so let's do that. So here's what we'll do today. So today we state a few more tests. And do examples. So what really happens here is you guys, it's sort of like integration. You get overwhelmed. You don't know which test to use. You don't know when to use certain tests. And the fact of the matter is all of that comes with experience. The more experience you have, the better. The more experience you have, the easier you recognize themes, the easier you recognize when to use or try a specific test. What you'll realize is sometimes more than one test can be applied to a particular series. So we hope that that you'll keep that in mind, and we hope that you realize, I say we, but I guess it's just me. Well, I do. I hope that those of you who want to learn this, put forth the effort and convince yourself that you're capable of making sense of it. So we gave an example, more to that point, we gave an example at the end of class on Tuesday where I said, okay, we'll think about how we can conclude. And we actually use this to motivate the comparison test. One of the things that you might want to do when, for a comparison test, well, in order to use a comparison test, you have to have a known entity. And so that is where your knowledge of, say, P-series and geometric series is useful. If you look at a series and it resembles sort of a P-series, then you might be able to use that to your advantage. So let's do an example or two of that. So here's the first one. And typically we would spell it out like this. Does a series converge? So does, let's say this creature. So it does 1 over k times 23 to the power k. So let's look at what's these guys look like. So does this converge? So does this, and what does it look like? When k is 1, you get 1 over 23. When k is 2, you get 1 over 2 times 23 squared. When k is 3, you get 1 over 3 times 23 cubed. That goes on forever. And just for full completeness, let's write out what these first 3 numbers are. So what's 23 squared? Well, you can do it in your head or you can do it on a calculator. You know, 20 squared is 400. And you can reason that way. Someone going to tell me what it is? That is so. So you should be insulted. Is it 596 or is it 529? See, now I'm insulted. So that would be 529 is the square root of 23, and then you multiply that by 2, you get this. And then we could even do the next one. And you get what? 1 over, I have to go to a calculator for this creature. This is 36,501. Does this guy converge? And it's not just enough to say that it does or doesn't. I don't need to know that you can flip a coin in your head. You have a 50-50 chance of getting it right. If so, why? If not, why? So part of doing this is understanding why things are true or why things are not true. I do know. Now, listen, one thing I should point out, me writing out what the series looks like, this right over here, you don't need to do this. I can analyze this series just looking over here. However, I think it's good practice if you're in calculus 2 or if you're any student to write them out just so you always remember what this symbol means. Okay, so here's my thought process on this one. There's a few ways I can go. My intuition makes me think this guy's going to converge. Now, the reason I think it's going to converge is because these numbers are getting small real quickly. And I know that's not enough to give us convergence, but it's a sign that it likely converges. So my intuition suggests this thing converges. And maybe even if you don't have intuition, maybe you go to a calculator and add up the partial sums and you say, okay, I think this thing converges. So how am I going to solve this? So my intuition says it converges. But that's not enough. Intuition doesn't get us anywhere. Well, obviously, Emily, you don't have the experience. So that's a good point. If you're going to say you don't have intuition, well, obviously, you don't have the experience. You're not supposed to look at this the same way I did. But what I'm telling you is if you right now you have 4 tests to consider. So you can think of it that way. What tools do we have to study this thing? Do I want to integrate it? Well, think about trying to use the integral test. That seems like a really weird thing to do. Do you want to integrate 1 over x times 23 to the power x? I don't think you want to do that. I don't even think you know how to integrate that. And so really, the only option that you really have at this point is the comparison test. So, if we're thinking of this problem as a problem in this class, the only tool that is applicable right now is the comparison test or the limit comparison test. And you can use either one, but I'm going to use the comparison test. So since this guy closely resembles this, I'm going to use the comparison test, but I'm going to try it first because I don't know if it's going to work. Sometimes the first thing we try is not going to get us where we want to go. Unfortunately, Zafalgar, that doesn't work. I wish it did. Now, are you going to think of it the way I'm thinking of it? Probably not. That's okay. At this point in time, you've had very limited, if any, practice. But my numerical, and I shouldn't say that. That sounds fancy. But my understanding of basic number, what I would call number sense, tells me the following. So note. Since we know that k is greater than 1, 1 over k times 23 to the power k has to be less than or equal to 1 over 23 to the power k. And if you're confused as to why, just do the cross multiplying. Everything's positive, so there's nothing illegal with doing this. And of course, if you still don't see it, then you could have removed the 23k. This is the same thing as this.
No, we made a mistake.
We did? Where?
No, we didn't. I'm sorry. Thank you.
I don't think we made a mistake. If we did, I'll have to go sit in the closet and think about all that I've done wrong. Do teachers still do that in like middle school and high school? Do they still like put you in the corner when you're bad? I used to love that shit. Like if you talk, they put you in the hall. Well, then you're getting the attention you really wanted, right? What am I talking about? All right, so here's what we go. Here's what we got. So we're done then. So we conclude that the series that we started with is less than the series of 1 over 23 to the power k, but this is a geometric series. And so let's remind everybody that this is this guy converges. And I guess I should be more specific, is a convergent geometric series. So this is what's most important in these types of problems, at least in my perspective, is that not only do you tell me it converges or diverges, but that you tell me why. You give me the logical reasoning, the sound reasoning. comments, questions?
So that statement does not mean that all geometric series are convergent, right?
No, no, we know all geometric aren't, but this one is, and this one's actually, again, why is this? So if you're still not sure why this converges, is note, if you need more reasoning, is that why does this converge? It converges since because R, which is 1 divided by 23, is less than 1 and greater than -1. Does anybody have a question? So, and by the way, just let me be even a little more clear. Notice 1 over 23k, if you're still having a hard time picking up what I'm putting down, this is the same thing as 1 over 23, the whole thing raised to the power k. Once again, you have certain exponential properties that often we forget. Okay, any questions about this thing before we do another one? All right, let's do another one then. So, how about something? Let's take, trying to think of a good one. How about k plus 1 over 5k squared plus 3. Does this guy converge? So the first term would be 2 over 8. The second term would be 3 over 23, etc. Does this guy converge? And then why? Yeah, you could use the limit comparison here. That's one way of doing it. And let's do it that way. So here's the way I might think about this. Since k plus 1 over 5k squared plus 3 is approximately So this is sort of my solution, I'm thinking. So since this is approximately k over 5k squared, which is 1 over 5k. So what is my reasoning here? This is my reasoning when k is large. What I do is I think the series will diverge. Now, why do I say I think it's going to diverge? So here's my reasoning. My reasoning is that this series in blue, when I go far out in the series, that these terms are pretty much the same as this. But I know the series of 1 over k diverges. That's the harmonic series. So I'm going to use I'll try the limit comparison test. With, I need to have two terms. My first term will be the one that I'm interested in. And my second one will be the one I'm going to use to compare. And let me remind you why I'm doing this. Why? Because I know that this series diverges. So I think that this term resembles a known series that diverges. So I think the one I'm after is going to diverge. So all that's left is for me to take the ratio of these two terms. That's what the limit comparison test says. And then it says determine what this number is. So let's do it. So we have to compute. The limit as k goes to infinity of a sub k's over b sub k. So what is this? Well, the a sub k's we know, k plus 1 over 5k squared plus 3. And then I'm putting this over 1 over 5k. It was plus 3. Not that that matters, but yeah. All right, well, now we just do some elementary algebra. I have a fraction over a fraction. That's the same as multiplying by the reciprocal. So I'm left with 5k times k plus 1 upstairs over 5k squared plus 3. And this is the same as 5k squared plus 5k over 5k squared plus 3. And we know that this limit is 5 over 5, which is 1. Now, what does this mean? Well, this means since the comparison, the series we're comparing with diverges, this means both series diverge. So both series diverge. Again, why do both? Because the limit comparison test says that if you take the terms of a divergent series, which these B sub k's are, these are the terms of divergent, and you compare them with unknown, that if this limit is between, if it's a finite number bigger than 0, that then they both diverge. So look, there's no doubt there's a lot happening and there's a lot for you to know and understand, and it's very overwhelming. I get that. I don't have an easy answer for you other than practice. Practice, practice, practice. Of course, some of you are like, I don't want to practice. And I understand that. I don't want to pay the water bill. I got to pay that. I don't want to pay the car payment. I got to pay that. I don't want to pay insurance. I got to pay that. Being an adult is a bunch of stuff you don't want to do. Anyhow, any questions about this? Okay, so it's time to sort of move on to the next group of tests. And it turns out we have 3 more tests to consider. But before doing that, so before we do that, let's make a useful definition. So we say that a series, which I'll write like this. So we take a generic series. So we say this guy converges absolutely if, when you take the terms in their absolute value, if this converges. So this is a very strong sort of notion, and we're going to illustrate what it means in a second. Unfortunately for most of you, that is English. So this is a type of convergence. It's sort of like we're adding an adjective to the convergence because it's a very sort of, it's in many ways, it's a stronger type of convergence. So here we're going to show you what it means in a second in a particular case. So So to illustrate, let's look at some old friends. So let a sub k be this, -1 to the k plus 1 over k. And then what's the absolute value of a sub k then? Well, that's just, the absolute value of -1 is just 1, so this just becomes 1 over k. So we get two series. The first series is this. So write this out. This is 1 minus a half plus a third minus a fourth plus a fifth minus a sixth. And that pattern continues. And then you also have, if you take its absolute values, you're just left with 1 over k. Now, we have names for these. This right here, as you guys know, this is called the harmonic series. And we already know it diverges. We showed that a couple classes ago. This guy, creatively enough, is called the alternating harmonic series. Here's a very, very useful fact. The alternating harmonic series converges, but the regular harmonic series diverges. Now, we're not going to show you the proof that it converges, but we're going to state a theorem that is the reason that it does. So the point we're trying to make before I state that is, notice that if I take the absolute values of this thing, it doesn't converge, whereas if I don't take the absolute values, it does. Yes. I'm gonna stand up while we do that. I need to stretch.
This is kind of my imbroglio, like
Say that again. It's kind of like what?
imbroglio, like absolutely confused. Like we say a series converges absolutely if the absolute value of that series converges.
Correct.
What we did, like alternative something, the next slide.
Yeah.
Please.
Yeah.
What we did, we said like absolute value of the series, like it is like harmonic series, it diverges, but the first slide says both must diverge.
Right, right. That's exactly right. I'm not saying that this converges absolutely. So that's the point of this example. So, okay, so maybe this will be more clear. So here you go. What does this mean? This means that this series, the alternating harmonic series, the one that alternates, it means this guy. So this might be why you're confused. It means this guy does not converge absolutely. So in this case, what we say is we say the convergence is conditional. Now, we're going to give you another example in a second where you will get absolute convergence. In fact, any series Defogger that has positive terms that converges is automatically absolutely convergent. So let me explain that real quickly. Note and this is for comparison. Let's say -1 to the k plus 1 over 2k. Let's take this guy. This guy, what is this? When k is 1, you get 1/2, right? When k is 2, you get -1/4. When k is 3, you get +1/8 -1/16. This guy converges. Why does this converge? This guy is a convergent geometric series. Okay. Now, take the absolute values of these terms. If you take the absolute values of these terms, it's still a geometric series and hence converges. Correct. I think that's what you're saying. So look, let's think of it this way. So if I go to the next page and I take the absolute values of that creature, well, the only thing that matters is the numerator. The denominator is already positive. So the absolute value of -1 is just 1. So this is just 1 over 2k. And this is 1/2 plus 1/4 plus 1/8, etc. This guy is also a convergent geometric series. So since both the absolute value of the terms and this terms without the absolute value, since both converge, what we say is we say that this series converges absolutely. So these are important examples, and what's happening, and you're confused for the right reason, because this is a very complex idea. It just is. So when you're a little confused, that's part of it. Part of the fun. Now, why do we want to distinguish this? Well, it turns out that it's, like most things, when we're doing math or science or really anything, we like to classify behavior. This thing floats, this thing doesn't float. Right? That reaction causes an explosion. This reaction doesn't. That animal can breathe underwater. That animal cannot. We classify everything. So why not classify things in math? Why not classify series that converge not only when taken as is, but also if we take their absolute values? And it's hard for you to see right now why that would be of use. But what happens, particularly in advanced mathematics and in places that use advanced math, two of the more familiar ones are physics and engineering. We have to consider these things. Some of you might know little things about, maybe you guys know some things about vectors and stuff. And not just calculus and math in one dimension, but maybe in multiple variables. Perhaps some of you studied that before. And what you'll know about that, if you do, is that we might want to sum up vectors. And what is the length of a vector? The length of a vector is its absolute value. So there are many natural reasons to want to take the series of absolute values of things, not just numbers. But you have to wait till more advanced courses. Yes, like physics vectors, that's correct. And even more general than just a vector from physics. What's quite fascinating is the higher you go in math courses, like for some of you, when you get to Calc 3 and beyond, when you take those classes, you'll realize how so much of this is interconnected, that you just don't realize it right now. So just to, you guys mentioned vectors, and it might be what kind of stuff? I mean, like, I don't know. I mean, like there's endless stuff. I mean, really, there's endless, all kinds of stuff that you can study in mathematics. Really, I sort of mentioned this to you guys before, and I don't mean to sound insulting, but in many ways, calculus, whether you're talking about the first semester, second, or third, it's really just fundamental mathematics. Now, you'll say most of your people in your life never even took calculus, and that's true, but most people in your life aren't studying university level physics and stuff like that, or in engineering. So in many ways, the math we're doing here is it's basic math. And I know I don't say that to be insulting, but it is. You can't go any further without a knowledge of all this stuff, especially in science and engineering. But real quick, let me point this out because you guys brought up physics, and this might be a nice time to remind you of something you're already familiar with. You just didn't think about it in these terms. So let's go to the next page real quick. So let's do a brief discussion. Some people introduce vectors in calculus 1 and 2. We don't here, but it might help illustrate some things to you. It might put things in perspective. So here you go. You're in 8th grade. You're learning about the Cartesian coordinate system, right? And you guys know that, let's say we take the point 2, 3. So you guys remember, as children, this is a ordered pair 2, 3, right? You go to the right 2 and you go up 3. Everybody's okay with that, right? Now, what vectors allow us to do is they allow us to also give not just sort of location to things, but they also allow us to associate magnitude and direction. So another way to think about this point 2, 3 is you can think about it as the tip of an arrow from the origin. So some of you, what you would do is that the purple sort of arrow is a vector. And maybe you guys would write it as X with a thing on it. You might write it as 2, 3 like this, or maybe you guys write them like this. So the point I am trying to make is that there is a very natural connection between points in the plane and vectors. And it's often lost on students why we need that. And it's again, when I teach Calculus 3, I try to make a special point that, that we can think this way. We can think about points in the plane as in lots of different ways. Another way, you know, you could think about this point is you could think about it on some circle of radius, whatever. And by the way, to continue with what we said before, well, the length of this vector which we usually denote like this, you'll remember what it is. You're taught in physics that it's this creature, that it's 2 squared plus 3 squared, right? Which of course is the square root. 4 plus 9 is 13. And you might not remember, or maybe it was never explained to you where that comes from, but that's just the Pythagorean theorem. Because if I make this right triangle, this is the side 3, and this is the side of length 2. So of course, this guy has length square root of 13. So what I'm saying then is these ideas that we're talking about series, they generalize to not just points in the plane, but also vectors. And then not just points in the plane, but points in 3-dimensional space and vectors in 3-dimensional space. You know, that's kind of hard for you to visualize, but imagine whatever room you're in right now, go look at one of the corners, and you could think about one of the corners of your room as the origin. And then you could put, you know, hold up my can of chemicals. You can imagine there's an invisible arrow whose tail is at the origin and whose point is at my can. So I can associate this can in space either as the point coordinates or is the tip of that arrow. And that makes doing things like physics much simpler to do, although it's hard for you to appreciate that. Does anybody have a question about this, by the way? So, yeah. And kind of what I'm saying, another way of thinking about what I'm saying is this idea, we go back to here with this, there's nothing that says that what we want to add up has to be numbers. If some of you get into advanced courses, you'll realize we have vectors here. We're adding up lengths of vectors, or we're adding up other abstract things. Believe it or not, we can, and you're going to actually see that we're going to do functions soon enough. Instead of adding up just numbers, we're going to have expressions here. So we're getting very general with all this. And so that's kind of why we need these ideas, which right now seem crazy to you and seem sort of useless, but it turns out they're not. So yeah, I mean, a funny thing about vectors is once you understand them, you're like, oh, of course, that's easy. But for most humans, it takes such a leap to get there. It just does. So you shouldn't get discouraged. You shouldn't think, oh, I'm stupid. I don't understand what's happening. Because that's really, it's really learning this stuff. I've said it before. I'm going to have to say it again. You know, learning this stuff is a process, and it's not just a process, it's a hard process. So learning science in general, you know, I always say it, it's not about how smart you are, it's about how willing you are to sacrifice your free time. Because nobody learns this stuff quickly. It is a process, a process, a process. All right, does anybody have a question about this? Comment?
I've got a question about
Yeah.
like, let's say, previous pages, previous slides.
Yeah, which one do you want
Like,
me to go to?
Like we said, we just say if this converges absolutely, if this converges.
Yes,
You remember that?
yeah, this page right here.
Yeah, this page. So this is wrong. No,
I'm not quite sure
This
what you
is-
mean.
is this a theorem or something?
No, this is a
I don't know.
definition. This is a definition.
But
I
we
am telling
proved
you.
that
Say that again.
prove that's wrong.
How do
Next
you?
slide.
We're
The
not
next
proving
slide.
anything. We're not proving anything. We're saying it's not doesn't meet the criteria. Let me explain this again. I am saying that take any series. This is your series.
Yep.
If it so happens that when you modify it and it still converges, then you say it is an absolutely convergent series. Again, I start with this series. If I take the absolute values of its terms and they converge, then I say that the original series converges absolutely. Now, what happens is at this point in the semester is most students don't see the need for having two different scenarios. Well, the point of me showing you this is that here's an example where it matters. This series converges. This one doesn't. And so what we're saying then is that this alternating harmonic series is not absolutely convergent. It doesn't fit the definition. It doesn't fit this definition. So it's not absolutely convergent. However, this series right here turns out that it is absolutely convergent. This one is because it satisfies the definition. It's not a theorem, it's a definition. These, and again, I don't want to keep saying this because I'm not trying to pawn it off, but this is conceptually, it's a difficult concept. It just is. And frankly, most students in Calculus 2 don't grasp it. And that's okay. We will literally, we're introducing this idea, and I have been fair with you. I've told you, hey, it's not that important in Calc 2, but it's very important later on. And so really that's all you should think about it. It's, you might only hear absolutely convergent a handful of times the rest of the semester. But it is something that we do need to introduce right now. And the reason that is because our next test that we study, the test that we are going to now do, well, not today, but tomorrow at this point, those guys actually can provide, these tests are theorems that tell when not only do we have convergence, but we have a stronger notion that is uniform convergent. So a way to think about this is as follows. So in many ways, absolute convergence is in many ways stronger than regular convergence. So another way of thinking about this is, here's a good sort of metaphor for it. Everybody that's absolutely convergent is also regularly convergent, but not the other way. So it's sort of like every square is a rectangle, but not every rectangle is a square. And again, I wish
Too
that there
much
was,
for a day. Too much.
yeah, I
for
know
a
it is,
day.
isn't it? Yeah, I mean, I'm not trying, and look, I'm not making light of it. I'm not telling you guys, hey, it's hard, ignore it. I am telling you that you're going to feel overwhelmed by it because it's difficult. It's just difficult. And it's probably one of those topics that at this level in Calc 2, you can just ignore. be completely honest. Well, I shouldn't say ignore, but it's, you know, it takes a little more time than perhaps you would want to spend on it to understand it. But again, the next couple tests that we're going to state, they're not going to just say something converges when they're going to say something converges absolutely. And so that's why we have to state this.
So this is not a big question. The biggest question right now is when we're gonna use which test. Like, how do we define
Yeah,
that?
that's
this
exactly
test
right.
is
And that's the hard thing. So here, you know, what we'll do is I'm gonna, like I said, I'm gonna assign a homework this afternoon and we'll talk about them. It's gonna be an ugly one because it's just gonna be a page of a bunch of series and it's gonna say, do they converge or diverge? And so what we'll do tomorrow in class is I will point out to them sort of what to look for and how to think about them. And hopefully that'll make it a little more clear on what you can do. Does that make sense? And again, don't forget the biggest goal of all. As you know, and in fact, Zafalgar, you're the one that made us aware of it a few weeks back. The ultimate goal in all of this is really not, I mean, it is important to understand these series, but our ultimate goal is to get at this thing called a Taylor series. That's the very useful tool. And that's a little less sort of, it's not as quite as difficult as this, frankly.
like a few years back, I just learned this all so easily. Like all of them, they were so easy. Right now, it is like, you know, it gets me absolutely confused.
That's okay.
Absolutely.
That's all right. That means you get to learn again.
Why not?
Yeah, that's good. That's good learning. Hey, that happens with, it's not just you that happens with, that's with everybody. Look, we usually, most of the time, if we learn something and we don't continue to use it, we forget how to do it. I mean, that's no different than walking or talking. If I stopped speaking for 6 months, I'm probably going to be real bad at it when I try to do it again. Math is no different. So you just got to keep that in mind and have confidence that, and confidence in yourself that you can learn it. All right, well, listen, I'm going to post some assignments shortly, and then hopefully you'll work on them, and we'll ask questions, and we'll give you some pointers tomorrow, okay? So does anybody have any questions, comments about any of this? All right, well, listen, thank you very much. Hopefully I'll see you guys in person tomorrow. That'll be the goal, but hopefully we do. All right, everybody, thank you very much and have a good Thursday evening. Oh, someone has something they want to say.
Bye-bye.
All right, bye, Bo. See you guys. Take care. Stay out of trouble.
Tomorrow
Yeah.
we're meeting in class, right?
Yes, classroom tomorrow. Very good. I'll see you then.
Okay.
All right.